I have two case studies. One very easy, select a salt. It's just to go into phase 1 studies. There are two things that are important: long-term storage as a dry solid and a fast dissolution in water. These were the two things that that needed to be improved. Materials were available, and they had an amorphous HCl salt with by HPLC 80% purity. The freebase which was made from this HCl salt was even worse. We can do a lot of to purify the product, but there is a limit, and the amorphous freebase was no good starting point for this kind of studies. So the approach was such that we isolated freebase from the HCl salt, and by a more controlled isolation, the use of different solvents, we had to look at what solvents to use. What we had was again an amorphous freebase, now improved purity, and there were no residual solvents present. So that was the first step to get a good starting material. 75% purity is still very low, and you have a lot of impurities there, so this is again not ideal to have a salt screen going on. So the next step, find a way to crystallize it. A small polymer study, in fact, or a small crystallization study to use 24 different solvents, and in the end what we had was a major improved purification step and a nice crystalline product of it. With this knowledge, we went back to the process and we implemented this purification step before the final step was done, because in the final step we could not combine the need what was for the process itself and a crystallization. So we go back one step, and there it could be implemented. There the main impurities were already present, and the purification was very useful at that moment. When you go to the crystallization solvent there, that one was also used as the final synthesis step of the freebase itself. After that, immediately the HCl's of the salt was prepared, so it could not be implemented as a purification there. Salt selection, because now we have a freebase which is nicely pure. 15 different counter ions could be used to improve the aqueous solubility. So we had already the first step that we have a stable form, but now the aqueous solubility was the main thing to focus on. We had two different solvents to produce. What we saw that some weak diacid, they bridge, they made solid material not that very crystalline, and it shows poor solubility, even worse than the freebase itself. But the very strong acids, and that in fact these were all but the HCl salt, showed nice crystalline material and an improved solubility there. So to see which of these strong acids to use, again a polymorph study was done. Everything was done in parallel here, and to find a good stable non-hygroscopic salt form. From that we checked which form we could use, and we went to TMP kilogram batch production, and in fact the process development itself took longer than the selection of the right form. So the form selection was no longer on the critical pathway of that development. We saw some problems with the starting material, and while doing these steps of producing, we also had an idea of how to select and which form to take. So you do not lose any time when doing it in parallel. Last case study is 8-step synthesis, but in this case the process itself was already a little bit fixed, but the final salt and the final conditions, the impurity levels, everything was already fixed of the final product. There were already tox studies done on this compound and they didn't like to repeat it. Of course, you need to avoid this kind of situation, but in this case we had to work with the result is already done. What were the issues? No crystalline intermediates, no scalable purification was available, and also the final step was not in a very acceptable solvent. So you have to dry a lot before you can even have an acceptable API at the end. This means that the whole process took a very long time, and still the purification, well, you don't want to have a column in it, but it was needed in this case. So the approach was that each of the 8 steps, we had a look, first synthesis, second solid state, and have a combined opinion on how to approach this step, how to optimize this step. First of all, there was a purification step. We had an intermediate oil, and what I stated before, we looked at the possible salts, so we defined a crystalline salt, and the intermediate could be isolated there. Of course, you introduce an additional step there. The overall yield was 3 to 5% lower, but now you have a purity of 98% plus each time and consistently, and you have a material which you can isolate, which you can say, this is our new step. You can see if everything, you have a better control on the process. So also the isolation of this was very fast filtration, so not really anything wrong with this purification step. It was just add counter ion that could be done without any other changes to the process itself, and instead of isolation of an oil, you get a crystalline salt. Another step was, well, it was an extreme slow filtration. It formed a thick cake of very fine particles sticking together, and as soon as the solvent was gone from the surface, water was attracted. So in fact, what you needed to do is a filtration with nitrogen flow on top of it, very controlled conditions. As soon as you slow down that nitrogen flow or remove it, you try to handle your compound, it liquidized immediately. So we use several common solvents there which were suitable for this step. First of all, you have a look at what is the chemistry, what can we use, and these were used to see if anything was done. So there were several solvents, as long as it was not an alcohol and you have a fine white product. When you use acetone, it even gave block-shaped crystals, and that gave a very fast filtration, but also no residual solvents. And again, within 1 to 2 weeks, we had the next step looked at. The chemistry was okay, but also the form that you get afterwards was okay. Finally, the final product, the salt formation itself, well, it was produced from dioxane, and that was actually not possible to do a good crystallization from. So we had a look at which you could use when you have a dry alcohol in the process. Then you can steer still on yield and the purity of your final product. So what the message in fact is that when you connect both the process development and the solid state chemistry, it shortens the timelines, but it gives a better process, and it also gives a better form. You don't need to repeat anything of your development because you have chosen the wrong form or you are stuck in your process when you start to scale up. What is also important is to fix the delivery method as early as possible. If you have an idea how to get it in at the place that you want to have it, that is very much depending what characteristics of your API you need. What do you need to improve. Of course, a tablet is different than a topical, and everything has its own optimization route, and it also has its own solid state part which can be applied to this compound. When you have possible issues in production, like a purification method which cannot be scaled, look at them, recognize them, and have an idea how to optimize it. When you control your crystallization, you already have, well, let's say, half of the work done, because you know what are the factors to improve your crystal size or your crystal shape. And finally, do not collect all information that you can, because it is possible, but collect these data sets that is needed to know and focus there on the appropriate what is needed to know. You can have a lot of data points and still not have the overview, but only look at what is necessary to do at the early phase. This was the approach of the combination of solid state and process development here at CML. And if there are any questions, please